Today we're here to talk a little bit about avoiding the no bid. So this is a presentation that's really specifically targeted towards contract manufacturers or people who are using additive manufacturing and specifically metal additive manufacturing to make parts for their end customers. I think it's a really timely time to be talking about this too, because we're seeing a lot of interesting issues arise around supply chains with the coronavirus pandemic and some of the difficulties that people have both in manufacturing and in getting parts. So I'm happy to be here to present on this. My name is Zach Murphy. I'm the VP of Technical Partnerships here at Velo3D. And so my role is basically to kind of help proselytize a little bit, do some missionary work, and kind of demonstrate what Velo3D is working on and how we can help specifically contract manufacturers expand the application space and really start to bring more parts into their business. As I was saying, it's a good time to be talking about this. Last week, I was actually on an interview, the 3D Pod interview with Mike Corliss, who is the VP of Technologies for one of our customers, Knust Godwin, which is a large machine shop, contract manufacturer in Houston, Texas. And it was interesting because they were asking Mike about how the current situation is impacting their business. And Mike said, well, on some of the more traditional manufacturing side, we are starting to see a little bit of a slowdown, but it looks like on additive manufacturing, things are continuing and maybe even picking up a little bit. And I think that really speaks to a lot of the advantages that metal additive manufacturing has. And specifically, some of those advantages are outlined here. And I think I'm speaking to an audience that knows these very well, so I won't belabor these too much. But when you're talking to a customer, it's important to understand their customers' needs, really. And for our contract manufacturers, their customers are the people who own designs. So the OEMs, the original equipment manufacturers, or other people who are trying to get an end part. And the goal often there is to optimize performance while reducing cost, or to at least maximize that ratio as much as possible. So when you look at the two things that we have here, kind of more towards the left, the ability to print existing and legacy designs where supply chain can become a problem is a way to reduce the cost. And the cost here is not just the actual dollar value, but also the lead time. Similarly, on the bottom, the combined assemblies is another way of reducing that cost, of reducing the total workflow of a part and the time and effort and money that it takes to end up with the end product. And then the other three categories here are really more focused on performance. So being able to print advanced complex designs out of materials that are traditionally very challenging to work with, like a titanium or Inconel or other nickel superalloys, is obviously very valuable. And then at the same time, lightweighting and some of the other advantages that metal additive has always purported to have can help with the performance as well, whether that's fuel economy for an airplane or specific impulse for a rocket engine. So all of these optimizations are really driving more and more applications to metal additive manufacturing. While that's true, there's also a challenge associated with it. So some of these same features that make additive manufacturing so attractive to the end customer also make it very difficult to deal with. And this is particularly true for some of the incumbent technologies. And what we've highlighted here on this impeller, on the shrouded impeller, are support structures. And support structures, as anybody who's worked with metal additive manufacturing know, can be very difficult. They're kind of a black art when it comes to designing support structures. Often they are the critical failure point, and they can limit the applicability of the technology to certain parts. If you've ever listened to a Velo3D presentation, you've no doubt heard us harp on the reduction of support structures. And really where we focused a lot of our conversations is around the low angles, being able to print low angles without supports. So you can see that here in the red pie slice where we have a picture of a shrouded impeller. And this is a part that in my time in additive manufacturing, I've seen people ask for quotes for over and over and over. And this is really a really good example of a part that is often no bid. So a contract manufacturer will say, this part, getting this part to the final customer requirements is just too complicated to be worth the trouble. There may be too much risk, too much workflow complexity, whatever the case may be. Or they do bid on it, and from a customer's perspective, it's just entirely too expensive to make sense to make with metal additive manufacturing. So shrouded impellers and low angle parts are really a critical part of what Velo3D is enabling. But then there are also several other parts that we are starting to see become more and more prevalent, especially with some of the capabilities that we're bringing to bear on the market. So heat exchangers, if we just go around clockwise, heat exchangers are a really great example. Large titanium parts, which may seem like a kind of interesting category unto itself, but I'll explain a little bit more as we go. Manifolds, and then tall parts, which is, again, kind of like the titanium parts, not really clear why those would be good candidates for no bidding on more of the incumbent systems. So just to rehash a little of what Velo3D really kind of built a lot of the business that we have on, low angle parts are kind of a critical limitation of incumbent technology. And shrouded impellers, as boring as they might seem, are really, really important. And they're found in applications through almost all of industry. So if you can make good shrouded impellers, they are really an ideal part for metal additive manufacturing. The problem with these geometries is that you have complicated internal flow paths where you often have a shroud that is a very low angle overhang. And if you're not able to print that without supports, you end up filling the part with supports, which can make it uneconomical to print or really kind of impossible because there's no good way to get those supports out of there. So the part that you see here was a part printed at Stratasys Direct Manufacturing, one of our customers, for Hanwha Tekwin. And they'll actually be presenting, I think, on this part specifically tomorrow. And it's a really kind of an amazing application for supercritical CO2 application. And this is a part that will spin at very high RPMs. They needed to do a lot of material characterization in order to have confidence in it, and then to be able to print it in a way that actually made sense. So I think one of the best images to kind of highlight the differences of printing with the Velo technology versus printing with a more conventional DMLS type of system is really the support structure. So here on the left, we have the support structure that Stratasys would have required to print it on one of their other metal additive systems. And you can see that the red supports, especially inside the impeller itself, would be very, very difficult to work with versus what they needed to print it on the Sapphire printer, which was far fewer supports and much easier to deal with and give them a part that met the customer requirements at the end of the day. But low angle parts are not the only thing that we do well. And we kind of wanted to emphasize some of these other applications because they're also very challenging parts that if you can print with confidence, you can start to really expand the applications that you're going after as a contract manufacturer. So the next is heat exchangers. And we have been working with a company called PWR out of Australia, which is one of the preeminent heat exchanger design and manufacturing shops in the world. And so they did a lot of testing of different technologies to kind of arrive at the final conclusion of purchasing a Sapphire printer. And the reason was that we were able to demonstrate class-leading thin wall capabilities. So print very, very thin walls that were liquid type. And that's really important here because in these applications, you don't want fuel mixing with your coolant or water in your oil or any other cross-contamination through the heat exchanger itself. And the reason that we're able to make that is the direct recoder. And this is kind of a critical enabling feature of our machine that allows us to print very, very thin structures and to do so without damaging them with the recoder. And so here you can see we have 300 micron leak tight paths and a number of different orientations, so kind of spanning all of the angular sweeps. The fins themselves are down to 170 microns, so incredibly thin. And they give PWR the performance that they really need to be an industry leader in heat exchanger design and manufacturing. So this is a really great example of how the Velo machine architecture can allow contract manufacturers or even OEMs really to print parts that otherwise would be very good candidates for not bidding on, just from the challenge and the potential yield loss of printing these parts leak-free. One of the categories that I mentioned at the beginning was also large titanium parts. And this may not seem like a very obvious candidate for passing on an RFQ, but anybody who's printed titanium, especially in laser powder bed processes, knows that titanium has a tendency to crack. So if you're printing large titanium parts or parts that have thick sections that are merging into much thinner sections, the part, if it's not treated right, will actually tear itself apart. And so before you can remove it from the build plate, you'll often have cracks that are going through the entire part. And this can be a real problem from a yield perspective. So a lot of times we run into contract manufacturers who would look at a geometry like this and basically say, thanks, but no thanks. I know that this part will cause me a lot of headaches, and I may end up actually being underwater on it at the end of the day when I deliver a part, just because of that challenge. Velo 3D has actually developed a way to print titanium in our laser powder bed system such that we don't get cracking. So we're actually able to reduce the cracking probability to the level that you can print a part like this without concerns. And so this part actually was printed the first time, printed successfully. And this is a picture of the machined part at the end of the day from that first print. So it's not only the low angle ports that you see on the inner diameter of this part that were important, but it's also the fact that printing a large diameter part like this is just very, very challenging. So again, this is a class of parts that with the Velo titanium printing become a much better candidate than they used to be for a contract manufacturer. The next category is manifolds. And manifolds are essentially a part with internal passages, fluid passages that connect in different ways. So we have a picture here of an injector. So this is a rocket engine injector, which at first glance may not seem like a really good candidate to describe manifolds. But one of the most important things about this injector, which was designed and made by Interstellar Technologies, is that it is a monolithic injector. So as far as I know, this is one of the only monolithic injectors that's been produced and hot fire tested. And that's really important because what they've done is taken all of the manifolding that would normally go on the backside of an injector and integrate it so that it's all printed in a single piece. So while you're just seeing the injector face in these pictures, what's going on behind it, and which is export controlled, so it can't really be shown in a presentation, is a lot of really amazing design work around manifolding to get the fuel and oxidizer to the injector face in the right manner. So this was printed as a single piece. Interstellar printed one on a traditional DMLS system and then printed one on the Velo 3D Sapphire system. And they found some pretty remarkable improvements from printing it on the Sapphire system. So they had a 5% gain in combustion efficiency, which, if you're not really familiar with rocket engines, doesn't sound like a lot. But 5% is a really remarkable amount of combustion efficiency gain, considering that it's the exact same part. There were no design changes between these two. So this extra 22.5 seconds of specific impulse is really pretty phenomenal and something that they were very surprised to see at the end of the day. And so this is kind of attributed to the ability to print these internal geometries very well with good surface roughness, good consistent surface roughness for all of the inner diameters. So horizontal tubes and some of the more complicated fluid passages can be printed without any internal support and with good surface finish on the Velo Sapphire printer. And so to talk a little bit more about maybe a more traditional manifold, this is a proxy of kind of an exhaust type of manifold. These are tubes that are printed. They're almost 50 millimeter diameter internal with no support structure. So this starts to give you an idea of maybe a more traditional type of manifold that can be printed successfully. And these are parts that are relatively common And if you're seeing these come through your shop and there's something that you're not really keen on printing with conventional technology, the Velo technology can really help to bring these into the realm of possibility. The limit here is also not 50 millimeters. We can print up to 100 millimeter diameter for horizontal tubes without internal supports. And then if they're angled, we can actually go quite a bit bigger than that. So there's a lot of geometries that are now really good candidates that you don't have to remove supports from the internal diameter after you finish printing. One other aspect of this part that's also pretty compelling is that it's very tall. So this part, as it's shown here on the right, is 16 inches tall, or nearly the full 400 millimeters of our Sapphire system build height. And tall parts are another class of parts that are traditionally somewhat risky to bid on. And the reason is printing tall parts can take a decent amount of time. And in that time, you're more prone to failure. Not only that, but a lot of the existing machines, some of the incumbent machines, are really not designed to print tall parts. So there are some risks associated with things like drifting, calibration drifting of the optic system, the recoder coming into contact with the part. Some systems even don't have enough powder in them to print their advertised full Z height. So you'll get about 3/4 of the way through a part and then have to stop the build, add more powder, and continue the build. And in a lot of applications, that's not acceptable. Generally, in aerospace applications, there can be no pauses in the build for it to be considered a successful build. So Velo3D really designed the system around being able to print tall parts without interruptions and without the need for pausing the build. But then we also built in things like the during build calibration. So we have the ability to check the alignment of the lasers to each other on every layer. And this ensures that there's no witness line where the lasers are both working together, and that calibration is maintained for the entire Z height of the machine, of the build. So these things, coupled with the ability to add powder live during the build and to change the filters during the build, means that you can start to produce these very tall parts with much higher level of confidence. So tall parts are not as risky as they once were, which really, again, brings them into the category of parts that you are confident to bid on going forward. And this is really important that we design the initial Sapphire like this, because the next step that we've taken as a company is to extend our Sapphire. So the current Sapphire system is a 315 millimeter diameter build plate, roughly 12¼ inches, with 400 millimeters in true buildable Z height. So it's almost 16 inches of true Z height. It's a dual laser system, two 1 kilowatt lasers. And one of the things that we've released, and that we actually have the interview that I was doing with Knut Godwin was kind of talking about, is that we have customers who've ordered our new 1 meter Sapphire. So this is a Sapphire 1MZ, which we'll be delivering to the first customers in the 4th quarter of this year. This takes the current Sapphire system and basically stretches the Z height to be able to build a full meter tall. It's almost 40 inches in height. It has the same process as the current Sapphire, the same in situ calibration, all of the same metrology and process control. So you have the same confidence in the parts that you get with the current Sapphire system, just in a much higher aspect ratio now. And we're seeing a lot of really interesting applications in oil and gas, in rocket engines, and some other pretty interesting components that really are not possible to be built in the current systems. And I think one of the other things that we wanted to mention here is that this is a production system, right? So this is not a custom machine. This is something that we're offering as a standard product offering. So now if you have a customer that's looking for these very tall parts, there is an off-the-shelf solution from Velo3D in order to actually print these parts. So I hope this has served as a good overview for the ways that Velo3D and our support-free technology can really help to widen the application space and the potential market of parts for contract manufacturing customers. And also, if you're an OEM and you're seeing this, I think it's really important to consider contract manufacturers who have Sapphire systems as potential vendors, because they will likely have a much better confidence in printing some of these more challenging geometries and be able to give you the parts that you're looking for at the end of the day. That's all for me. I'm happy to answer any questions. Thanks for attending.
Hi, Zach. Thank you. All right.
Yeah,
So we have quite
absolutely.
a few questions for you in the Q&A. So first one, since
All right.
Sapphire systems can adopt parameters based on the geometries, will there be any effect on productivity, like build rate? Also, what's the surface roughness can be achieved at low angle surfaces?
So for the first question, there's definitely, different processes run at different rates, right? Your core process runs at a much higher rate than, say, like a contouring process, if you're looking at kind of a volumetric build rate. So there are differences between the different processes in terms of the build rate. I think one thing that's really important to mention is that when we're building like our very low angle surfaces and the geometries that incorporate those, while the build rate drops a little bit, it doesn't drop dramatically. And that's a really important thing if you're looking at parts that people claim have been built with laser powder bed that are very low angles. Make sure to look at the throughput, because one of the tricks you can play is to slow it down so that you're printing just incredibly, incredibly slowly. And you can start to get away with some of these geometries, but it's just not economical to print if that's how you're actually approaching it. And then on the second question, for a very low angle surface, if you're looking from like the 10 degrees down to a 0 degree overhanging surface, our surface roughness there is probably between like a 10 to 15 micron SA in terms of the actual measurement.
Thanks. Another question for you.
Yep.
Hi, Zach from Priyesh. Could you speak about the orientation used to print the shrouded impeller? Also, does the Sapphire employ additive melt pool monitoring?
Yeah, absolutely. So just to show you the actual orientation, what you see here on the right is the orientation. So it's printed flat. You're printing basically with the rotational axis of the impeller aligned with the Z build direction. And this is how we prefer to print rotating parts such as shrouded impellers, because it gives you better axis symmetry of the part, and it makes it more rotationally symmetric, which is really important when you're spinning something at 40,000 RPM. Regarding melt pool monitoring, we absolutely have melt pool monitoring, and I think the more important thing than just the monitoring is that our Assure quality assurance software is actually interpreting that data and giving the user actionable feedback around defect detection, both in terms of the porosity of the part, so the probability of pores being formed in the core material, and then also from surface roughness. And so like in a manifold, when you have internal diameters that are very hard to kind of scope or CT, depending on the material, our system actually can show if there are surface defects that are caused by, as an example, like a melt pool instability. So those are two very powerful metrologies that come with the Sapphire system.
Another question with quite a few votes. What does a non-contact...
Yeah, it means exactly that. So our recoating system lays down a layer of powder without actually touching the plane on which you're lasing. So in kind of a more conventional system that you might be used to, what the recoater is doing is basically snow plowing powder across the bed. And that applies a shear force to the part underneath it. So when we talk about our free-floating build capabilities, one of the really important things there is that we're starting without any consideration of what's below the part. So lately I've seen some support-free parts where really they're printing the part kind of inside a holster. And the reason they have to do that is that the recoater applies force. And so there's no way to really build a truly free-floating part in other systems. Whereas with our system, the ability to lay down powder in a very consistent bed without applying any force gives you the ability to print low angles, to print free-floating parts, to print very high aspect ratio parts, such as in heat exchangers. And it's really kind of a true differentiator in terms of system architecture.
Awesome. Another one. TIE 64 can be adversely affected by O environments. What is the environment for Sapphire?
Yeah, that's absolutely true. And I think it depends on the grade of the titanium, the TIE 64 you're working with also. So like in medical orthopedics, when you're working with grade 23, with a very low oxygen content, it's important to be printing in a very controlled oxygen environment. So our system's designed to be able to run below 10 ppm oxygen in the build chamber. Often when we're running titanium, we're running it in a actively controlled oxygen. So we'll run at something like 150 to 200 ppm, depending on what the desired outcome is. But actively control that so that you know for a fact what the oxygen is and can keep it at a very, very low oxygen level throughout the entire build.
What kind of materials are you using other than titanium?
So right now we are printing an Inconel 718, Ti-64, both grade 5 and grade 23. We recently released our aluminum parameters, which is F357, which is like a aluminum silicon 7. And we're developing right now Hastelloy X, and we'll likely have 625 out in the Q2 or Q3. Great.
We'll end with one last question from Melanie Lang. Do you attribute success with titanium to in-process monitoring and control or other factors?
Some of it's due to in-process monitoring and control. I think the biggest thing is, I guess, the second half of that, which is process control. So cracking of titanium is due to the way that it cools down, essentially, and the residual stresses that are incorporated into the part as the part cools down. And if you can control the cooling rate, then you can start to eliminate that as a source of potential failures.
Well, thank you so much, Zach, for joining us today.
Absolutely. Thank you for having me.